Hello and welcome back. We're going to continue with the plate girder design. This will be part 2. Last episode we did the cover plate, and today we're going to go ahead and design a plate girder. So take a look at the problem. As we go along, I'll put stuff on a board so you can see where everything comes from. We have this beam is about 70 feet long, and we want to design a plate girder for it. Possibly 60-inch would be good. And normally the depth could be anywhere from 1/6 to 1/15. In this case, for 70 feet, it comes out to 1/14. So the dead load given for this particular situation is a 1.1 kip per foot, not including the weight of the beam. And the life load is 3 kip per foot. A 36 steel. But before we go ahead and calculate the moment and shear, let's find out the approximate, as close as possible, the weight of the beam, and then we can add that into it. Okay, so we're going to build this girder from ground up. We're going to use this 60-inch, we want it to be 60-inch tall. That means the girder, the web plate is going to be probably 58-inch from here to here. And then let's say we're going to make this about 1 inch right here. Let's say we're going to 1-inch piece of plate. Let's guess at 15 inches. Later on we can figure out if it's how close we are. And let's calculate the weight of this whole thing here. So we got two 15 inches by 1. And that's going to be 2 of them. And the area is going to be 1 times 15. So that's the area. And we know steel is about what? 490 pounds per cubic feet. And this is 1 times 15 is an inch. So let's make that to divide that by 12 times 12, 144. So it's the area comes out in a square foot, and multiply by 490. Then plus the web, let's say, is a 3/4 inch thick, which is 0.75, multiplied by, and that's going to be instead of 60. So take 2 inch off, will be 58 inch. That's the area of the web, and divide that by 144. And multiply by 490, and that the weight of the steel come out to 250 pounds per foot. So now we have that. We'll go ahead and calculate the shear and moment, but first we're going to find out in a load resistance factor design what our load is going to be. Let me just get rid of this right here. We're going to have 1.2 times dead load. So WU is equal 1.2 times dead load is 1.1 plus 250 pounds, 0.25. And then plus 1.6 life load, which is 3 kips. And that comes out 6.42 kip per foot. So let's stay here. And the maximum moment for a shape like that, it's going to be mu is equal WL squared divided by 8. 642. And multiplied by L is a 70 square, 70 feet square. Divide the whole thing by 8. And that comes out to 3,039.32 kip foot or foot kip. So the shear, which is the reaction right here, that comes out WL divided by 2. We're going to say RU is equal WL divided by 2. W came out 6.42, multiplied by 70, divide that by 2, and that's 224.7 kip. Going over to allowable stress design, that's going to come out to WA is equal, basically we're going to add the load. It'd be 1.1 for a dead load plus 250 pounds for the beam weight plus life load of 3, and that comes out to 4.35 kip per foot. So our moment, MA, comes out to WL squared divided by 8, which is 435 times 70 squared divided by 8, and that 2664, that's a foot kip. And shear is going to come out to WL divided by 2, W is 435, L is 70, divided by 2, and now we have, what we have here is the moment due to applied load for the load that we designed for. Because we know the moment, we said, okay, for this type of moment, what is the required plastic section module? And we take it from there. So we're going to say Z required, that's a ZX, and we know the formula, which is a mu divided by phi times FOI. So our MAU comes out to 3,932. 3,932. Remember, it's a foot kip. And divided by 0.9 is a phi, and FY is 36 KSI. KSI. So we got a problem here because this is an inch, that's in a foot. So let's multiply this by 12 to make that to an inch, and therefore our Z gonna come out to 1456 inch by power 3. Next thing we want to find out, we want to make sure this web right here that we have come up with, 58-inch web, it's compact, that meet the requirement of AICE. And that is based on table, you can see on the board, table B4. And in order for it to become a compact, it has to be less than 3.76 of square root of E divided by FOI, and that is the case 15. So let's go ahead and find out what that is, and we can figure that out. We have H divided by TW should be less than or equal 3.76 times square root of E divided by FOI, and this is really a number that you really should know instead of calculating many times. So that comes out to 3.76 times 29,000 KSI divided by 36. And that number comes out to 106.7. So what is our H divided by TW? We said that our web is about 58 inches. That's our limit. We knew that. But one thing we don't know, how thick we should make this member. So at the beginning we guessed that. I said, let's make it 3/4 inch so we can guess at the weight. It's not 0.75. Let's find out what is the minimum that we need to do to satisfy this requirement. So we know our H, which was from here to here 60, minus 1 inch here, 1 inch here, so minus 2 inches, and that's a 58. But our TW that we require is basically the this number divided by that, so that will be 58 divided by 106.7, so that's 0.544 inch. And normally when you, around here in the United States, when you get a steel, you're going to go by what is, they have a standardized sizes. It's a 5/8, 9/16, 3/4, and something like that. And what this number come out too close to, and don't be afraid to go a size higher, so you be sleep better at night. In this case, say, okay, let's go 9/16. Is 0.56. Our plate, it's going to become here, it's going to be that is a 9/16. So this plate is going to be basically 58 by 9/16. And then H over TW comes out 58 divided by 9/16, and 103.1, which is less than 106.7. Too close, but let's just go ahead and follow this for now. Erase the board, and then we can continue. Oh, we know this section is compact. We want to know if we need any stiffeners. In order to have a requirement for stiffeners, two things are going to happen. Number one, from section G2, note number 2 that reads, it's on a board, it says it has to be the H over TW got to be bigger than 2.46 square root of E divided by F of Y, which this number comes out basically 2.46. That's a 4 square root of 29,000 divided by 36, and H over TW, it has to be bigger than that, which is 69.8, and we just calculated this a while ago that I erased it, that came out to 103. So this is a 103. So this says we require to put transverse stiffeners. However, but you got to meet the second condition. The second requirement is our web. We got to find the capacity of the shear in a web, and that capacity, if is less than that, right here, they say the shear applied by the load, then we say, okay, stiffener is required. But if the capacity of the web itself is bigger than this, then we don't need it, because we know the web is strong enough. So let's go ahead and get to work. Capacity of the plate, for this web plate is VN is equal 0.6 Fy area of the web times CV1. So we got to find CV1 before we can use this equation. To find CV1, we're going to go back to the spec in G2 section, and that is going to be a G2.1. So our H divided by TW, which is equal 103, it should be bigger than 1.1 square root of kV E divided by F of Y. And now we have another unknown kV. Looking at the same spec, kV is equal, given to us by that spec as 5.34, which is equal 1.1 times square root of 5.34 times 29,000 KSI divided by 36, and that's 72.15. All right, therefore now we know that, and we got to find out our CV. So now that we have met this condition from G2 -4, we have CV is equal 1.1 square root of kV times E divided by F of Y, and divide the whole thing by H divided by TW. And plug in all the number we have is 1.1 times square root of kV came out to be 534, and 29,000 KSI divided by 36, and divide the whole thing by to 103, H 103, and therefore our CV comes out to So now we're going to go ahead and calculate VN, and VN is equal 0.6 times 36 is FY, and that's that equation. AW, area of the web, we said it was 916 times 58, and multiply CV1 is 0.7. Comes out to 493.1 kip. So okay, so this is, I had to erase the board, I need some room here. So this came out to our shear capacity of this plate. But because we're doing both load resistant factor design and allowable stress design, so we're going to bring it over here, and we're going to put our factor of safety into it, or resistant factor to it, see how it's going to be. So it's going to be phi VN is equal 0.9 times 493.1. That comes out 443.8 is way more than 224.7. Therefore, using load resistant factor design, no, we don't need any stiffeners. So if we go to allowable stress design, it's going to become Vn divided by omega, and that was 493.1 divided by 1.67, comes out to 295.3, which is bigger than 152. So checks out, we don't need any stiffeners. So now we're done with that. Let's go focus on a flange. I want to know what the area of our flange is. We guessed at 1 by 15. So the area of the flange is given by the equation. It's on a board. Let me write it down here. So it's going to be AF is equal mu divided by VB. So the area is of the flange is given by this, and mu came out to be 3932. And be careful, that's going to be a foot kip. So we got to make sure we divide it by 12, make it an inch kip, because everything else is an inch. And divide that by 0.9 times 36 KSI times H plus TF. Our H came out to 58, and our TF is 1 inch. And then minus TW, which was 916, multiplied by H squared, 58 squared, and divide that by 4 times H is 58 plus 1 equal 16.66 inch squared. And we said what by 115, so our assumption was kind of not good. Let's change that to a number. Let's go a couple number high up, say 18 inches good. Okay, let's try 1 by 18, so make this 18 inches. So now we have come up with the size for the flange, which is 1 by 18. Want to make sure it's compact, just like we did with the web. Go back to the table again, B4.1, case 11, it says B over T has to be less than that to become compact. And this number comes out to 10.9. So what is B over T? Our B is 18 inch. Look at the picture. The picture shows, says the B is from here to here. So it's basically 18 divided by 2. That's our B, divided by T, and T is 1 inch. So that comes out to 9, and 9 is less than 10.79, so we're good over here. We have designed this, we come up with this shape here. Let's find out what is the actual Z of this shape is. And Z is equal, and we talked about it, first we got to find a plastic neutral axis. So we got 2 plates, there's 2 of them, 2 times, and the area of the plate is 1 by 18. 1 times 18, that's the area of the plate. Area of the plate, or it'd be the flange in this case. And then the distance between center of this and right here is this distance is 58, so that's a 58 divided by 2 times 58 divided by 2, and the center here is about, this is 1 inch, so it's half an inch. So 58 divided by 2 plus half inch plus 0.5. So the next thing we're going to do the web. So the area of this area right here, this right here, which is 2 of them, it's going to be 1 and 2, let's say 2 plus 2, and the area is 9/16 times 58 divided by 2. So that's a 58 divided by 2. And the distance from here to there is a 58 divided by 4. And 1535, which came out bigger than 1456. One of the things, let's check in, because I want to convert this back to a moment, see if it's going to make it, which normally does. If it's going to beat this, then it's okay. But we said it was, I erased it. We said the steel, that the way we had it was 250 pounds. Let's see what the exact weight of this steel comes out to be. So we had 9/16 times 58. That's the area of the web, and divided by 144 plus, the plate was 1 by 18. 1 by 18, there was 2 of them, times 2, and divided by 144 and multiplied by 490 pound per cubic feet. So that comes out to 233 pound, which is less than the 250 that we guessed originally, which is okay right there. And we now want to know if this, what is this Z doing here? So now our MN is equal Z total, which is this right here, right there, times FOI, which is equal 1535 times 36, and that comes out to, let's divide this by 12 first to make it a foot kip, and 4605, 4,605 foot kip. Check my number, and then we're going to come back up here. Phi time MN is 0.9 multiplied by 4605, 4144.5, which is bigger than 3932, so we're good. And back in here, we want to double check it. We're going to say M divided by omega comes out to 4605 divided by 1.67, 2757, which is bigger than 2664, and checks out.